to our application is, well, create the data frame. To create a data frame, we need to give it a schema. And our data frame will be very simple. It will only have two fields, one called A of type integer, and the second one called B of type double. Pretty simple. We are building this data frame here inside our application. This is not something we usually do in a Spark application, but this is just basically a hello world in Spark world. And our data frame will have 3 rows, first with 2 in the field A, 3 in the field B, and so on and so forth. And the same thing in Python. Exactly the same thing. We also need to define a schema. We also adding some rows to this data frame and returning it. And lastly, to actually run our application, we are defining a main method. It needs to accept some command line arguments, but we won't actually use them in this code. We are creating the Spark session. We are creating the data frame. We are printing in schema. This is what we want here, and we are showing the data frame's contents. And for the sake of completeness, we are stopping the Spark session. Same in Python. Apart from, we don't actually need to create a class for that. We are fine with just functions. And this does the same thing. How to run it? Well, I'm assuming here that we have a working Java on our machine and that we have Scala installed. We need some basic, pretty simple configuration file. This is basically it. It just defines some dependencies. We are using Scala build tool, SBT, which does pretty much what the name suggests. SBT package creates a jar file, so it packages our code together with these dependencies, and we will be able to run it later. Exactly here. Another utility is Spark Submit, which can run either locally, can run our code locally, but it will also be used to deploy our Spark applications to some bigger clusters. We need to pass it the path to the jar file. We need to point it at the class we want it to use, and that's it. And for Python, I'm also assuming a few things. I'm assuming we have a working Python installed in a relatively new version. Other than that, we can just pip install PySpark and run it. Of course, I recommend it using virtualenv for installing, but yeah, you see. And we can just call our module just as any other Python module, and it will run our Spark application locally. The result of these invocations will be this. First, we see some information about compiling, blah, 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 some wording, some information. I don't worry about it. And then we are seeing the schema and the contents of our data frame, exactly what we wanted. And here is Python. So basically, we see the same output as we would expect, because yeah, this is exactly the same code, only in different languages, right? Well, almost, but yeah. What typically happens in Apache Spark? Well, if we are coding only in Scala, in general, the flow looks like this. We have Spark contexts. Well, the Spark session contains something Spark context. And this whole JVM process is called a Spark driver. It uses Spark executors, which are separate JVM processes, to do the actual job. When it communicates with the Spark executors, and if it needs to send or receive any data or pass it UDI, I will come to this later, it needs to serialize and deserialize this stuff because it gets transferred over the network, for example, because this is a distributed system. But for Scala, or when we are writing code in Java, this is basically what this diagram looks like. For PySpark, it gets two more things, because, well, Spark, when we are writing in Python, in PySpark code, this is still a JVM application. And to be able to communicate at all with Spark from Python, we need some translator. And this is basically what this Py4j is. It's a translation layer for us, or rather for PySpark, to use Spark. To be precise, Py4j allows Python to interact with JVM objects and vice versa. In our case, we are defining the data frame, the data frame locally in our driver in this Python module, this Python process, and this data frame for Spark to do anything with it, it needs to also gets first translated to JVM stuff and then serialized to get to be passed to Spark contexts. And then when we are receiving any data back, it also needs to go over the same process. So this adds additional overhead right away, even before we are actually using executors. The previous slides with code could lead you to believe that this is very similar process for both Python and Scala, and these are actually two very different languages, believe me or not. And the first difference for me is typing. Scala is strongly and statically typed. The main thing for me that comes with it is that many errors that we will make during the development gets detected in the compilation phase. So way before we deploy our code and it will crunch some numbers. Python is also strongly but dynamically typed. For some definition of strong and dynamically, don't email me about it. This means that to be equally sure in our code, to be equally sure that it works correctly for our data, we need to write more tests and apply more static analysis. And by the way, I strongly suggest using optional type hints, not only for writing PySpark. It can make our life as a developers much easier if we also use correct tools afterwards. MyPy basically, or other type checker. About development, Spark offers us a few choices of APIs. We don't need to use all of them. We will be mostly fine with just one of them, but it's a choice. These are just tools we need to use. The most basic ones are RDDs, which offers us a few very basic operations on the most low-level structures within Spark. There is a data frames API, which I used on the previous slides to demonstrate the data frame. This is higher level concept above the RDDs, and it contains quite a few options to do the actual data processing. There are also datasets, which are statically typed, and as you would expect, they are available only in Scala, just because only Scala from these two choices is typed statically, and we cannot have it in Python. There's API called Spark SQL, which in some regards is very similar to data frames, except the syntax, but it gives us similar possibilities. And there are UDFs. For cases where above APIs are not enough for our use cases, and we need to write some arbitrary code to do our data processing, we can define our own functions. In Scala, these functions get executed in the same JVM processes as the rest of the data processing within executors. In PySpark, things get more heavy. Because this diagram grown a little, for executors to be able to run our Python code, our Python UDFs, it needs to have Python. It needs to spawn additional Python processes. Moreover, it needs to also pass the data to these workers. So this is another layer of serialization and deserialization of our data. So this is a necessary overhead to run our PySpark UDFs. And the more PySpark UDFs we write, the worse for our performance. Performance isn't everything, though. Ecosystem. When we are considering the choice between Scala Spark and PySpark, we need to also look wider what both ecosystems are offering us. And with Spark itself, there comes a few libraries, for example, for structured streaming and for machine learning. These are both available in Scala and in PySpark. There's also GraphX for graph operations. It is only available in Scala and not yet in PySpark, but we are waiting long enough to see that it probably won't happen. It is because Apache Spark is written in Scala. So just by design, any feature will be first available in Scala and maybe later in other languages. On the other hand, there's a wrapper around GraphX called GraphFrames. I haven't used it, but yeah, you can try. So there are some workarounds, probably with some performance impacts, but I don't know. On the other hand, Python ecosystem is pretty large, like outside of Spark. It offers us many tools and frameworks, and yeah. So some things to consider when choosing one over the other. On the yet another hand, if you have that many, Scala is not really that niche of a language anymore. It's also grown when speaking about ecosystem. I don't want to enumerate and compare it actually, because there's no general answer to what is better. I want you to think about what are benefits of a given ecosystem, given a project that you are working on. So yeah, it's a typical "it depends," but that's reality. Think also about what would you need to do in a components just next to your data processing jobs, and how would it affect your choice of either Scala or PySpark. Modularization of your system helps, of course. You can split your system so that you can have numbers crunching in Scala and some machine learning stuff in Python just next to it, with passing the data through some storage. That's a common thing, I think. Also, think about your team's competences and what your team wants to learn in the future. What does it want to maintain? What will your future teammates will probably know or want to know? Okay, back to some more low-level thinking. How do we deploy our Spark applications? Well, at the most basic level, we are deploying a jar in Scala. Our jar, something called fat jar, is our code bundled together with the dependencies. In PySpark, we have a few options how to distribute our dependencies of our code. We can put it in zip file and transfer to, for example, a Hadoop cluster. We can build a virtual env and pack it and send it over to the cluster. Or depending on our setup, we can install these dependencies directly on the cluster. I mean, depending on the setup, because maybe you are using ephemeral clusters in the cloud, or you are sharing the cluster with other teams, and you could have dependencies clashes. So yeah, but these are the options. The actual deployment looks pretty similar in both cases. We are using Spark submit. We point it at the cluster. This is the -- master argument for both cases, and then we are pointing it at our code, just like that. We have our code. Even before we have our code, we need to already think about the maintenance of it. So again, think about how the choice between Scala and Python will affect this maintenance. What your team is what is versed in, what does your team know about either Scala or Python, how will it affect your I don't know, future agility, velocity if you prefer, and what are the aspirations of your team? Maybe someone wants to learn Scala on the side, and yeah, maybe this will affect the choice somehow. Think about collaboration. Usually, your team maintains the team's code, but there are sometimes cases where you are collaborating with other teams. My team is only one of many in Allegro, and mostly we are maintaining our own modules, our own components. But we also collaborate strongly, in some cases, with a research team. And my team is mostly about JVM, but the research team is much more versatile in Python. And this sometimes affects the choice of technology here. Sometimes it makes sense to first use PySpark for the collaboration part, and maybe then rewrite it in Scala. This is some valid option. When thinking about maintenance, it's hard to not think about the language itself. Again, the first thing that comes to my mind is how typing looks like in either option. But there are, of course, more. And there are a few other things that impact our maintenance burden, our agility, our speed of development. What can impact our work is the popularity, and not the popularity itself, but first, how easy it will be to get help, get support for our problems, get support, for example, within an organization or on Stack Overflow or anywhere else. And second, how easy it will be to, I don't know, hire someone to work on our problems. Yeah, I looked at a few developer surveys. On the previous versions of this presentation, I showed some numbers, but yeah, it pretty much boils down to there's not enough data in these surveys to actually tell what's more popular, Scala, Spark, or PySpark. So I only am showing you this. I checked how many questions are there asked on Stack Overflow for these tags for Scala and Apache Spark, and yeah, and the numbers look like this. I hope you can see it. It's not exactly 50-50, but for me, it's so close to it that it doesn't really matter. Both are very valid choices from the perspective of popularity. So it's not a differentiator for me. And I think, last but not least, the performance. That's why we're here, right? So I performed a benchmark. I just did a simple select from one of our, let's say, bigger tables and saved it in another place. And the numbers looked like this. And why are they looking like this? Because I used a data frame API, and when we are using the data frame API or RDDs, it really doesn't matter which language we are doing it in when we are having a non-zero, let's say, amount of data. Because Spark will do exactly the same thing anyway. It is just instructed to do it in different languages. So okay, let's do another benchmark that will actually tell us something. Let's, in the middle of this, let's add a column through a UDF in Scala and in PySpark. So I did just that, and I added a column in Scala, and it on the same data, and it took 2.5 minutes, and in PySpark it took over 4. What does it tell us? Well, that adding a column through the UDF in PySpark is slower, but only and only this. Don't look at such benchmarks too much, because while they can help you with building an intuition about some specific single small parts of your code, how this small piece actually represents your whole code. How well does the benchmark represent your data also? So as soon as you see this, it can tell you that, well, yeah, adding a column through the UDF is slower in PySpark. But as soon as you are doing it on other data, or as soon as you are making any other operation, I think such benchmarks are pretty much useless. Also, when trying to choose, think about your performance requirements, whether you actually have performance requirements. Again, for us, some jobs in Allegro do have an SLA. They need to finish by some time of the day. So this is a pretty solid performance requirement. It's a strong signal that the code should be performant enough. Some jobs don't. They just need to run. So there is not such signal. And while we can look at this number, well, we can look at how fast the job is. It would be just a number that doesn't help us much, and it will steal our focus from other, maybe more important things than just the speed of our job. So, it pretty much is impossible to give you an answer how to choose, well, which one to choose, because it depends. But it depends on what? Well, I would first point you at your functional requirements. Your job actually needs to do something, right? To serve some business purpose. Second, sometimes you actually have performance requirements, and this is a pretty strong signal as soon as it's real, not only ambitional. Think about the competences of your team, of the maintainers of the code, both existing one and possible future ones. And think about other non-functional requirements for the code that will affect your development. And I think I'm done here. You can find the slides on this under this URL. Also, remember to visit allegro.tech where we have our tech blog, podcast, and quite a few other things. And I believe we have a few questions, right? Thank you.
Yeah, we have a couple of questions. The first one is about deployment. You already mentioned a little bit about deployment. Maybe you can elaborate how to deploy PySpark to production, Kubernetes cluster versus client mode.
Mm-hmm. We are using ephemeral data pro clusters in Google Cloud, mainly, not only. Our ecosystem is like diverse enough to not have anything in 100%, but mostly we are using Google Cloud's ephemeral clusters. I think client mode, but again, there may be some other use cases I don't know about. So I think mainly client code, at least in the code I'm familiar with.
Okay, thank you. How do you orchestrate workflows of PySpark jobs in Python?
Mm-hmm. Another Python thing called Apache Airflow. And also we are using Google Cloud for that. It has a managed service for Apache Airflow, but yeah, Apache Airflow all the way.
How would you practice PySpark at home without access to big data?
Mm-hmm. That's a very practical question. A few cloud providers have some free tiers that you can use, but also be very cautious about not running over this free tier, because it can cost you quite a lot. I think our development machines nowadays are big enough to simulate, like, not big data, not really big data, but something that we can actually learn on, let's say, using, I don't know, some local setup of Yarn cluster, or I don't know, maybe Kubernetes. I'm not sure. I would be happy to hear your ideas.
What kind of data do you crunch at Allegro?
I'm not sure I can offer you anything more interesting that I can tell you, but no, I don't think I can honestly answer that.
Big data.
Mostly, yeah, 90%. Sometimes this is not really big data, and you need to see. You need to be aware when not to use big data tools.
So how easy it is to pick up Scala if you're Python dev on a scale from 0 to 10? It depends, isn't the answer.
How easy? 10 being easy, right? I don't know, 6. 6.5. Depends
how you understand 6, yeah.
Okay, it's hard to quantify, but yeah, I think I'm pretty productive after like two years of learning Scala this way, because this is exactly me in this question. I'm a Python dev coming to Scala to Scala team, let's say, and yeah, it's 2/3 on this scale.
Okay, that's it. Thank you.
Thank you.